I don't think you're going to be disappointed. We're probably going to go short today. It's two reasons. One of them is I just didn't get to do enough preparation. The other one is I started looking at the next section on the method of undetermined coefficients. It's not the way I remembered it, so it's going to take me a little longer to work that up than what I thought. Okay, so any questions first? Seemed like there was something I wanted to tell you that was not, I don't know. If I come up with it, I'll think about it. Oh, yeah, let me go ahead and do this. Yeah, that's what it was. Didn't get a chance to type this up anywhere. So here's some assignments. Page 164, numbers 5, 12, 14, 19, 28. Now this one, do like I did, just use the Wronskian, the determinant thing I did on the example the other day. I think it works better than their just kind of general way of doing it. And 39 and 43. Okay, now that stuff all has that doesn't have complex number roots. Okay. Now on page 172, okay, 3, 14. Now not all of these are real long, and you know that some of these where we're coming up with general solutions are just a matter of, you can solve the quadratic equation and you basically just write the answer down. So I know this looks like a lot, and it is, but they aren't all long. I really am glad that we're out of the stuff we done on the first test where the problem's just really long and messy. Okay, so this is the section where they do, the second section is where they do the complex solutions. And I think there's some just general, then they're kind of mixed up in there too. There's some in here that aren't complex number solutions as well. Okay, let me get things arranged here. Okay, so let's just do a little bit of a reminder of what we're after here. The main problem is to solve something like number 1, where we have some function, unknown function y. We know that it's first and second derivatives follow this, are linear, and they have constant coefficients. So y double prime, by prime, cy equals some function f of t. And to solve that, first we need to look at the simplest case where the f of t is 0, the homogeneous form. And the way to solve that is to look at the auxiliary equation, which is an ordinary quadratic equation. And we had the following sort of things. If this equation, the auxiliary, has 2 real roots, R1 and R2, and I'm just writing down what I had the other day, then a general solution is y equals C1 e to the R1t plus C2 e to the R2t. If equation 3 has 1 real root, so it's a repeated root, in other words, it's a perfect square, in the general solution is y equals C1, oops, let's call this the repeated root r, e to the RT plus C2T, e to the RT. And then what we've been working on, looking at is looking at the complex case. 3 has 2 complex solutions. Then general, and they're of the form alpha plus and alpha minus I times beta. Then the general solution is y equals 1 e to the alpha t cosine beta t plus C2 e to the alpha t sine beta t. Now it's a good exercise, and I probably should assign it. I don't know, maybe I'll stick it on the next test or something, is to show that these pieces here actually are linearly independent. Because that's the whole idea on this, is we've got a second order DE here, so we get 2 solutions, 2 linearly independent solutions, and you combine those to make the general one. And I don't know, I didn't read the section real carefully because I'm skipping a lot of the theory in this section. But to show that those 2 are linearly independent using the Wronskian is a nice little exercise. It might show up sometime. Okay, so that's what we're doing. So we're talking about the complex situation in particular now, and let's do one. So a couple more examples. Page 172. Solve the initial value problem here, where I didn't do this one the other day, did I? I don't think so. I had it on my list, and I've lost my notes. Well, there it is somewhere. I don't think I got to it. Solve this initial value problem. So we'll find the general solution and then use the values y prime to figure out what the constants are. Okay, so we'll do the auxiliary equation. Auxiliary equation here, well, A is 1, B is -2, C is 2, so it's 1 r squared minus 2r plus 2 equals 0, which I'm going to solve by completing the square. Because that doesn't take any more time than using quadratic formula. So get the constant over on the right hand side by itself. Add, take half of 2, take half of the r coefficient, square that and add it to both sides. So half of -2 is -1. When you square it, you get a +1, add it to both sides. So the left side is a perfect square, and the right side is -1. And so r is the plus or minus square root of -1 plus or minus I, and we get from that if you add 1 to both sides, r is 1 plus or minus I. Scoot that over a little. I'm going to need a little more space down here. This is not a hard problem, but it takes some space. Things on the board a little better here. Okay, so our complex solutions, remember it's alpha and beta here. So alpha is the real part, that's 1, and beta is the imaginary part being the coefficient of I, That's also 1. So the general solution is y equals c1 e to the 1t cosine 1t plus c2 e to the 1t sine 1t. And we get the C1 and the C2 by looking at the initial value parts here. You first look at a problem, you think those are kind of funny numbers, but no, they work out. So when you plug a pi in, we should get e to the pi. So that's C1 e to the pi cosine pi plus C2 e to the pi sine pi. And fortunately, some things go away here. So e to the pi C1 e to the pi times cosine of pi is -1. And this is all 0. So the sine of pi is 0. So let's see, we have e to the pi equals minus C1 e to the pi. Okay. So that's enough to tell us that 1 is negative C1, or in other words, C1 is -1. Okay, so that means we have then our function looks like that then. Negative e to the t cosine t plus c2 e to the t sine t. And our other part of the initial value had to do with y prime of pi equals 0. So we have to take the derivative of this one, and it's going to be a product rule problem. Derivative of the first times the second plus the first times the derivative of the second. Okay, so that's negative e to the t. That's the derivative of the e to the t part times cosine. And now we take a negative e to the t, and the derivative of cosine is minus sine. Okay. And in the second one, the derivative of c2 e to the t, c2 e to the t, so take that times the sine. And then we take the first term, c2 e to the t, times the derivative of the sine, cosine. Plug in what we know. If you put a pi in there for t, we should get 0. So minus e to the pi cosine pi will be plus e to the pi sine pi. Okay. Okay. I'm sorry. Let me just go ahead. Well, yeah. I'm sorry. Okay, so I now plug in a cosine pi. All the cosine pi's are -1, and all the sine pi's are 0. So negative e to the pi times a negative, this is -1. This is going to be e to the pi. All of this stuff is 0. And over here, C2 e to the pi cosine pi, well, cosine is -1. So this is a minus C2 e to the pi. Is that right? Yeah. So when you add C2 e to the pi to both sides, you get C2 e to the pi equals e to the pi. So that means C2 is 1. So there's our solution. And yeah, the DE part doesn't take very long. It's just a little bit of algebra it takes there. One of the things you got to be willing to do on these is you got to be willing to be, you know, work messy little problems and be careful. If you're one of these people that does his homework in ink, then don't make mistakes. Yeah, I don't mind it. I mean, I know people that work crossword puzzles in ink, but you just need to get it right the first time. Okay, so that's just a typical sort of problem. And let's see, let's work a few more here. What have I got? Uh, Now, I gave an example last time, and I'll do another one here for higher order uh, linear DEs with constant coefficients. So this is number 29. Now, the book has an odd notation for the fourth derivative. I put up what I consider to be a standard notation, but he actually has some sort of notation I haven't seen before. He has y with an IV as an exponent. I mean, the main thing is you don't want to put a whole lot of dashes down there. Most calculus books I've looked at use, if you've got more than 3 derivatives, you don't want to put more than 3 primes on your y. So they'll just put the little thing in exponents. So I've rewritten it this way to match what I'm more used to. But he has yiv, which means fourth derivative. We're going to find a general solution, so it won't take long to do this. The problems get lengthy when you do you're finding a particular solution with initial values. But this won't take too long. Auxiliary equation, well, it's fourth power, so this is going to be r to the fourth plus 13r squared. And remember, the y doesn't correspond to anything. The r only corresponds to derivatives of the function. So our auxiliary equation is r to the fourth, 13r, and plus 36. Okay. And can you factor that? I hope. Sure. Since it's r to the fourth and an r squared, if there was an r cubed and an r and stuff in there, we'd have a little bit of trouble. And they have some like that. They have some fourth degree, well, some DEs that give you fourth degree polynomials that are kind of interesting to try to factor. But we need factors of 36 that add up to 13, so 4 and 9. And set the first factor equal to 0. R squared plus 4 equals 0, so you get negative 4. Take the square roots of negative 4, both of them, plus or minus 2i. R squared plus 9 equals 0, so r squared equals negative 9 plus or minus the square root of negative 9. So you get plus or minus 3i. Now, in terms of the complex numbers, both of these are purely imaginary, which means if you write them in the way the book was writing the solutions, there was alpha plus or minus I beta. Well, there is no alpha here. Well, there's alpha. Alpha is just 0 in both cases. So we're going to get two solutions or two parts of our general solution are going to come from the first factor and 2 from the second. So let's see if I can just write down the answer here. Okay, from the first one, we get C1. I'll put the e's in, but they don't amount to anything. E to the 0t cosine 2t plus C2 e to the 0t sine 2t. That's what comes from the first factor. Plus, we get a couple of more solutions from the second factor. We get C3 e to the 0t cosine 3t. Actually, it doesn't matter which one goes first. And a plus a C4 e to the 0t sine 3t. So, simplifying this, C1 cosine 2t plus C2 sine 2t plus C3 cosine 3t plus C4 sine 3t. So as I said, we just once you get your equation down, it's just a matter of solving that. And the solutions you just write them down. Fortunately, we don't have initial values to go along with this because it would be a real mess if we did. Okay. Yeah. Let's see. This just made me think of a problem. Well, maybe I'll go ahead and do this. I'm assigning number 27. So, which is in this, well, 27 is in a different section, but it is a higher order. It's a third order. So, let me say a little bit about that. Let me scoot on over here and get a blank page here. Problem number 27. It's a initial value problem, so it's going to take you a while to get your final answer because it takes a while to figure out what you're going to have 3 constants. But I'll go ahead and do part of the work for you. So that's the DE you're going to be solving. So you're going to have an auxiliary equation of r cubed minus 4r squared plus 7r minus 6 equals 0. Now, I'm not going to solve this, but we have to figure out how to solve that thing. It has, one of the solutions is really nice. So let's just make, and I was thinking about this when I was working, and I said, does this thing factor? Well, it does, but I don't know that you're going to just come up with it. So let's just make a little note here. So say if you have a polynomial, if p of x has p of, say, some number equal to 0, then x minus that number is a factor. Okay. So if you can figure out where this equation equals 0, if you can get one spot where that's equal to 0, that'll get you started on the factors. And do you remember how to do long division of polynomials? If you can find the number, a nice number where this thing equals 0, and you can, you may need to get your calculator out and graph it and find a solution from that. And then say check that to make sure it's really a solution, because it's that you're not rounding things off. But then you would divide whatever that is into your, well, so if we're doing r here, I guess we've got it. If you can find some sort of solution for this auxiliary equation, then long division polynomials will give you the other thing. And this will be something with an r squared in it. And what that means then is whatever this polynomial is, that's something you use quadratic formula on. So it may take a little bit of trial and error to figure out what is this number. But take this thing, find out where it's equal to 0, whatever it takes. It is a nice number. Then once you have that, do the long division. That gives you a factor. When you divide that into the r cubed thing, you're going to get an r squared. It's going to go into r squared number of times with some other stuff. Okay, second degree, and that's something you use quadratic formula on. So if you can get one solution, you can find where it's equal to 0 one place, that gives you a starting point. And you're allowed to use a calculator or something, because I looked at this for a while and I couldn't see offhand how to factor it, but it does factor. Okay. All right, so what I wanted to say a little bit now about is, let's go back to what we started the chapter off with. One of our motivations for looking at these second order constant coefficient DEs was the spring mass damper system here. And this is the picture I grabbed, but it looks like the one in the book. Remember, M is the mass of the object that we're moving around. B is the damping force. It generally works opposite the velocity. And K is the spring constant. And F of T is some sort of outside force that's acting on it. Something might be giving it a little extra push or a little extra pull or something. If there are no outside forces, because that's what we're looking at now, is when this right-hand side is 0, then this is what our equation would look like. Now, what I'd like to do, and I might be asking too much here, is we can solve this equation, and we might actually solve it here in a minute. But let's see if we can figure out what this, think about this as a spring mass damper system. What does it mean? What do these numbers mean? In a practical sense, what does y of 0 equal 2 mean? What does y prime of 0 equals 0 mean? Okay. So let's remember the picture. I didn't write it down here very well or draw it very well, but y of t, which we're trying to find, is the position of our, well, I guess, of our mass at time t. In particular, it's the position, the beyond equilibrium. I mean, so to say y of 0 equals 2, what does that mean? At time 0, let's say that, let's say that right here is the equilibrium. Okay, so if the thing is sitting there, it's not going to move. There's no stress on the spring. So when I say y of 0 equals 2, I mean that at time 0, what? Remember, this is position. So at time 0, we're over here someplace. We've stretched this 2 units beyond the equilibrium. Okay. So we are the mass equilibrium point. Okay. Now, what does y prime of 0 equal to 0 mean? Well, you had it closer to right at the very start. Okay, well, y prime is velocity. All right. So this means that initially there's no velocity. In other words, we just let go. We don't take it out here and give it a shove. We've stretched it out 2 units, and then we just let it go. Okay. So there's no initial velocity. Well, when you let go, it's not moving immediately when you let it go. I'm just letting it go. I'm not giving it an extra shove this way or an extra shove that way. So the initial velocity equals 0, so you just let it go. We've pulled it 2 units beyond equilibrium, and I let it go. Okay, so that's what those two things mean. And I don't like this picture a whole lot. I prefer the picture, the vertical sort of picture. Okay. So, in other words, we've stretched this thing down a little bit, and we let it go. Okay, if y prime of 0 was something else, then that means we would stretch it down and give it an extra shove down or an extra shove up or something. Okay, but we just, giving it a smack. So we stretch it out here in 2, and we let it go. We don't shove it back in or push it out. Okay, so that's what the initial situation is. Now let's think about what the DE says. Okay, I've got a picture hidden here, and I don't want to. I think I've got it. Every now and then I hide something in the screen, and I forget where I put it. There it is. I want that. So, not ready. Okay. Okay, so I'm just copying down the spring mass damper equation here, and we see that there's no y prime term here. We have a spring constant of 16, which we can figure out what that meant there. But b is equal to 0. So this means no. That b was the damping constant, which might be friction or it might be something else. You might have this thing attached to some sort of piston that's working like a shock absorber. There's no damping. Right. So the situation is then, okay, my little picture that I redrew that I lost again here. There it is. It's not supposed to quite look like that. There's no outside force acting on this thing. Okay, so there's no force over here. There's no damping in here. We've got basically a frictionless surface. Okay. So what do you think it's going to do? I pull it out 2 units and let go. Okay, and then, well, of course it's going to go back, but then what's it going to do? There's nothing slowing it down. No, why would it accelerate? Yeah. But there's nothing that's going to slow it down. It's going to go back and forth the same amount every single time. If there was damping on there, it would slow down or it wouldn't go as far. But there's nothing slowing it down, and my picture isn't very good here. But if I pull it out 2 and let it go, I bet it's going to go back here from 2 this way to 2 this way, and then back, and then back and forth like that. And so that's kind of what they want on these problems, is to look at this, figure out what it's going to do before you solve it. Okay. And we can solve this. This is going to be, I don't really want to do too much. This is r squared plus 16 equals 0, which gives us 0 plus or minus 4i. So we end up with something kind of like, well, this part of the previous problem, this part. So we're just going back and forth with cosine and sine. There's nothing that's making it slow down or speed up. Okay. Is that one okay? Is that all right? Because the next one was one that just really kind of got me. I thought, let's try this. This is what we're going to end on, is try to analyze the motion for this thing. In the same section, so we're going to try to figure out what this differential equation corresponds to on a spring mass damper system. And we can understand the initial value stuff pretty easily, because this, like the other one, we're pulling if this is a spring, and this is equilibrium point, we go one beyond it. So here would be 0, and here would be 1. So we bring it out to 1, and we let it go. So we're stretching the spring. If it was a negative 1, we'd be compressing it 1 unit beyond equilibrium, and then let it go and see what happens. All right, now the what happens part is what kind of got me on this one. Okay. Now, if there was no middle term, this thing would just oscillate back and forth. There wouldn't be anything to slow it down here. This I found to be a very curious number. They stick a couple of these on here. The damping force here is negative. Now remember, what generally damping works opposite the velocity. But this is actually working in the same direction as the velocity. So this force, I mean, if the spring thing is moving back that way, it's actually going to kick it in a little extra force. B is negative. This is the opposite of the usual damping. What we think of as damping. Okay. So you still have a spring constant, but that middle term is a positive B. If you go back to when we originally set things up, okay, that meant it was a negative B on one side because it went opposite velocity. When we brought it over, anyway, this is the opposite of what we usually think of as damping. So we're going to have a force acting on, or it's going to apply a force in the same direction as the velocity. So the damping force, I'm going to put this is in the same direction as velocity. Okay. So what do you suppose that would do then? It's not going to slow something down, it's going to speed it up. Does that sound reasonable? As I said, when we let it go, it's going to want to head this way. And because of what we're calling damping here, what this middle coefficient does, it's going to actually push it even further. So I don't know, at some point it might override the spring constant, but instead of just going back and forth the same amount if there isn't any kind of damping, this is actually going to push it maybe like that, maybe even worse. Okay. And what you'll actually see when you work this out is, well, something like that, or maybe even worse. This is the auxiliary equation factors as r minus 2, r minus 4. Okay. So you get two solutions. And so your general solution is y is some constant e to the 2t plus some constant e to the 4t. Okay, we can figure out those constants from the initial values, but what do these guys look like? What is e to a positive power function and e to a positive? Those guys both look like this. So this thing isn't going to oscillate at all. Okay. When you let go, the spring's going to start pulling it, and this damping type force is going to start pushing it back in that direction. And it's going to go nuts. And we may have to, I mean, we'd have to figure out exactly what those constants are to get a good picture of it. But the damping force is not going to slow it down. It's going to actually cause it to speed up, and which means this isn't even going. There's no sine or cosine in here. This guy isn't going to oscillate. It may. Well, let's go ahead and finish it off. It doesn't take long, does it? Let's see what those constants look like, and then we'll actually graph this thing. Let's say y of 0 equals 1. So that's c e to the 0, c1 plus c2 e to the 0. So 1 is c1 plus c2. Y prime of 0 equals 0. So the derivative of this, oh, I should have done y prime first. It's going to be 2c1 e to the 2t plus 4C2 e to the 2t. So you put a 0 in there, you get 0 equals 2C1 plus 4C2. 2C1 plus 4C2. Yeah, I hadn't planned on solving this, but we can. So we get that on this one we get 1 minus C2 equals C1. On this one we get minus 4C2 equals C1 equals 2C1. In other words, minus 2C2 equals C1. Set these two things equal. 1 minus C2 equals minus 2C2. So we get that C2 is negative 1. Yeah. And you get, I think, C1 is 2. Now, I can't pull up the calculator. But if somebody could pull up their calculator and graph y equals 2e to the 2t, not 2e, c1 is 1. C1 is 1. Negative. C1 is 2. Yeah, I'm getting right here. 2e to the 2t minus 1 e to the 4t. Tell me what that looks like. The calculator never works in this computer. So yeah, put in x instead of t, but let's see. And start at t equals 0. We don't care what's going on over here. Okay, so we start at 1. So we're starting at time 0 here. We're at 1. So we'll forget about what goes on the left. It does that. Okay. So that's a really awful graph. So as time passes, as t goes to infinity, y value goes to negative infinity. So think about this, and it's impractical if you think about our picture, because here's our spring, here's our mass. Okay, this thing's it's gonna hit that wall. Okay, but it's headed in the negative direction, and nothing's gonna stop it. You let it go over, it starts heading in the negative direction. It stays going in the negative direction. Okay, so that's takes a little bit of analysis on these, but I think that's what they're after, is to look at this, and in this case, the damping force is opposite of what we usually think, and damping is generally in the opposite direction of velocity, but if b is negative, then it's in the same direction of velocity. So the spring is not going to be enough to stop it. Okay, so you got some problems to work on now. Let's see, today is Thursday. Let's see if we can have those in a week. May not. But some of them aren't very long, and some of them are. And we're going to talk about the circuits next time. I'm going to do number 33, which analyzes a little more vibrating spring with damping. You're going to do 32, which has a non-damping spring. And then I'm going to look at problem number 34, because vibrating springs are standard application of this sort of thing, but also electric circuits are as well, with the resistance and capacitance. And in the meantime, I'm going to look at this undetermined coefficients and see if I can find a better technique than what they do. And I'll see you then next week.